think we have just one more reaction here with these anhydrides, this aminolysis. And here we're going to take get our acyl chloride, and it looks like we have ammonia here, and it says 2 equivalents, and we end up forming an amide and ammonium chloride. So the mechanism here is going to be just like what we saw already. So acyl chloride, now we have a nitrogen as a nucleophile instead of an oxygen. Can attack tetrahedral intermediate. We're going to kick out our good leaving group. And then to balance this, we could have our chloride pull the proton off. So that we have our amide. And here, notice we generated HCl again. So that's the problem practically, or in the lab with these acyl chlorides, is we generate this strong acid, which we might not want. And that's what this 2 equivalence is all about. So that what we could do is have ammonia, I'll write it down here, another equivalent of ammonia react with HCl. Oops. In an acid-base reaction to generate NH4 plus Cl minus. So it's going to trap the HCl as the ammonium chloride as the salt here, so that it's going to prevent the reaction from becoming really acidic. Now you could use pyridine if you wanted to, but if you have an amine here, like ammonia as the base, why not just dump in more ammonia? So that's why you see some of these differences from one reaction to the next. And so here it makes more sense just to add more of ammonia. Ammonia is cheap to bubble into the reaction to help to form this amide. Now, if you had a really expensive amine, it took you a month to make, you might not want to waste an entire equivalent of it, an entire mole of the amine compared to a mole of this. So then you might add another base to mop up the chloride that you're actually forming, the HCl. But that's why you see here is the 2 equivalents. Okay, so why don't we mention one more reaction here with the reduction, and then we can pause for just a couple minutes, if that's all right with everyone. Some time goes by quickly. So we've seen reduction reactions. We've reduced aldehydes and ketones. I haven't used this color for a while. So remember, we had a ketone. I have LiAlH4 here. We could use LiAlH4 in ether. Step 1. Step 2, adding a little bit of water or acid. We're going to generate our alcohol. So we could reduce an aldehyde or a ketone to the alcohol. This reaction is suggesting that we can take our acyl chloride, lithium aluminum hydride. It says 2 equivalents or in excess, again with ether. And it looks like we go all the way down to a primary alcohol. So let's see if we can come up with a mechanism for that and squeeze it in a very small amount of space that I left here. So this lithium aluminum hydride was a way of generating H minus here, hydride. Let's just, for simplicity, let's just write H minus rather than drawing the whole lithium aluminum hydride structure. So we're simplifying this mechanism. We can imagine this attacking the carbonyl carbon, tetrahedral intermediate. Now, hydrogen's a horrible leaving group, but we have our chloride, we have a good leaving group. So let's kick that out. We've reformed the carbonyl group. And then now notice what we've done is we've gone here from our acyl chloride, starting material, and we formed an aldehyde. And we know that aldehydes can be reduced with lithium aluminum hydride. So let's have another equivalent of hydride attack. It's going to squeeze its way under the name, or on top of the name, form a tetrahedral intermediate again, O minus. Put both of the hydrogens here to help show that. Now all we have are bad leaving groups, horrible leaving groups, 2 hydrogens and a methyl group in this case. So we don't have anything else that can happen. So we're just going to wait until we add some water to the reaction. And then from our primary alcohol. So we'll see in a couple of places, coming up soon also with a Grignard reagent and things like that, that sometimes we'll end up having the reaction happen 2 times with something like this acyl chloride. So that's why we have 2 equivalents, or you might just add excess, 5, 10 equivalents of it, so that you're not getting a mixture of products, hopefully. But notice the reaction mechanism that unfortunately is kind of squeezed in here. It's the same thing 2 times. So hydride's attacking our acyl chloride, tetrahedral intermediate, and then when we kick out the chloride, we form an aldehyde. And so we know aldehydes can be reduced with lithium aluminum hydride. So the reaction happens again, hydride attacks the aldehyde. Now we've generated the tetrahedral intermediate, but we no longer have any good leaving groups, and so then we're going to protonate to form the alcohol. So reduction reaction, new starting material with the acyl chloride, but same mechanism that we've seen before. Here is the second part. The last thing to mention here is there are ways that you can actually stop at the aldehyde. That if you had an acyl chloride and you wanted to reduce it, say, only to the aldehyde, what you'll end up doing is using a sterically bulky reducing agent. And I didn't want to take the time to draw out the mechanism for these reactions, but just so that we're aware of these. And so if you see them in your reading, these are 2 commonly used bulky reducing agents. And so you'll notice they look like lithium aluminum hydride, except having 4 little hydrogens around the aluminum. We either have these isobutyl groups from the species that's known as dibol H or dibol, where we have these 2 isobutyl groups kind of protecting the aluminum, and there's the hydride that can be donated. Or this species here, which still can be a hydride donor, and this lithium is terpenoxy aluminum hydride. But the hydride here is surrounded by all of these isopropyl type group. I'm sorry, terpbutyl groups surrounding the aluminum. So what these reagents do is they react with the acyl chloride because it's so reactive. So even though they're sterically bulky, it still allows you to reduce the acyl chloride. But the aldehyde is not quite as reactive, so you can actually kind of stop the reaction at the aldehyde. So as an example, on the bottom here, if we had this acyl chloride here, and you wanted to reduce this only to the aldehyde, you would use something like diba H or diba to then generate the aldehyde. Mechanism is similar to what we've seen. We're not going to worry about that. There's coordination of the aluminum to the hydroxyl group, but I just want us to be aware that if we were to use lithium aluminum hydride, this acyl chloride will go all the way down to the primary alcohol, the OH here. But if you use something like these 2 reagents listed here on the top of the page, you can stop at the aldehyde. All right, so then we have